Hey guys, so it's Jason Matthew from Trinidad and Tobago, and welcome to the BiochemJM YouTube channel. So let's get straight into it. So today we're going to be doing gluconeogenesis part 1. There will be 3 parts, so part 2 and part 3 will be up shortly. So gluconeogenesis can be split into 3 parts: gluco, neo, and genesis. And genesis means to make, neo as in new, and gluco, sugar. So you are making new sugar. Alright, and that's basically what gluconeogenesis is. Gluconeogenesis is the formation of new glucose from non-carbohydrate sources. 90%, so in other words, the significant majority of gluconeogenesis will occur in the liver, while a small amount will occur in the kidney. It involves both cytosolic enzymes as well as mitochondrial enzymes. Alright, so a few things to think about for gluconeogenesis. Alright, we are making new glucose from non-carbohydrate sources. It involves both cytosolic enzymes and mitochondrial enzymes, which you should realize is different from, let's say, glycolysis, where all the enzymes are found in the cytosol. The next thing I always tell my students to do is to ask yourself, in which state, in other words, is it the fed state or in the fasting state, gluconeogenesis will be taking place. So the idea here is that if you want to get new glucose, it has to be that the glucose levels are low, and you'll get that in the fasting state. So we'll talk a little bit more about that very soon. So look at this graph here. So we are saying that gluconeogenesis is important in maintaining blood glucose during the normal overnight fast. This metabolic pathway is very important because glucose is the primary energy source for the brain and erythrocytes. It's especially important for the erythrocytes, alright? And again, gluconeogenesis is taking place during fasting. Alright, now the brain and the erythrocytes are particularly sensitive in that they need glucose. Alright, the glucose levels in the blood should not drop because they need glucose. They use glucose as their primary energy source. Now I'll point out something now that we'll come back to later when we do lipid metabolism, and that's that in a severe jam, the brain could start using ketone bodies as an energy source, right? It doesn't want to, but in prolonged fasting, alright, during starvation, if the brain is not getting enough glucose, then it will say, alright, I'll compromise and I will use ketone bodies as an energy source. Alright, but here's the thing, erythrocytes, they can't use anything but glucose as an energy source. And the reason being is that there is no organelles in the erythrocytes, the mature red blood cells. Alright, only glycolysis could take place, and you need glucose for glycolysis. So the only source of energy, the only means of erythrocytes getting ATP is through glycolysis. So they must always get glucose. So it is extremely important that we maintain this blood glucose levels. And how do we maintain it during our overnight fast? Via gluconeogenesis. So let's look a little at the graph now. Alright, so you see here exogenous source, so that will be from your diet. So you now had a meal, you're very happy and nice, the blood glucose levels will spike and then it will start to drop. Alright, in the early stage of fasting, the glycogen in your liver will be broken down to glucose to maintain the blood glucose levels. Alright, so in that, at the beginning of fasting, that's the point of this. At the beginning of fasting, the glycogen in your liver is going to be broken down, alright, to get glucose. Now remember, there are 2 places where you can have glycogen. You can have glycogen in the muscle and you can have glycogen in the liver. It is the glycogen in the liver that we are breaking down. We are metabolizing the glycogen in the liver to maintain blood glucose levels, not the muscle. Alright, the glycogen in the muscle is not used to maintain blood glucose levels. Please remember that. And this glycogen breakdown is useful in the early stages of fasting, just at the beginning. Alright, now these glycogen stores, they are not indefinite, they are not infinite. Alright, they're going to be used up, and they are used up quickly. Now the next thing I want you to appreciate about the graph is this. Now if you look here, you see that blood glucose levels are being maintained by the breakdown of glycogen, but eventually gluconeogenesis is going to be the one that's really going to be responsible for maintaining blood glucose levels during fasting and prolonged fasting. Alright? Now, the body doesn't wait for all the glycogen to finish and then gluconeogenesis. If you watch from the graph, gluconeogenesis is steadily increasing. Right? So it's to maintain an average blood glucose levels. Because if the cells were to wait until all the glycogen was used up and then start gluconeogenesis, then there will be a sudden drop in glucose in the blood, and that would be very bad for you. So these two pathways, although glycogen is the main one at the beginning, gluconeogenesis is steadily increasing, alright? And then eventually all your glycogen sources, alright, your glycogen stores will be totally depleted, and your gluconeogenesis will be there for the long haul in maintaining blood glucose levels. As I said, it is very important that we maintain blood glucose levels for the brain and the erythrocytes. So let's imagine if you start to become hypoglycemic and there's not enough glucose reaching the brain, well then those brain cells won't be able to get enough energy and you start slipping into unconsciousness, and if left unchecked, coma, and if that's left unchecked, well, 6 feet under the ground. Alright, so let's move on. Alright, so glucogenic precursors, and the three common ones would be lactate, glycerol, and glucogenic amino acids. We get lactate from fermentation in the red blood cells and muscles. Alright, glycerol comes from the degradation of fats in the adipose tissue, and glucogenic amino acids, I'll talk a little bit more about that very soon, but two very common examples of glucogenic amino acids, and I put alanine and aspartate also because we're going to see them when we do nitrogen metabolism. So just keep that in mind, alanine and aspartate. We're going to come back to that in my course later on. Something I want you all to note, acetyl-CoA is not a glucogenic precursor for mammals. Alright? We cannot convert acetyl-CoA to glucose. A point I should make is that plants have an additional pathway called the glyoxylate cycle that can allow them to use acetyl-CoA as a precursor for glucose, but we cannot. Animals cannot use acetyl-CoA as a glucogenic precursor. Plants and other microorganisms can, not us. Alright, so there's something to remember. It comes in a multiple choice. So glycerol as a glucogenic precursor, and we need to know the reactions. Alright, now for my course, I won't burden you all with learning these structures, although I would recommend that you do because it makes you understand the chemistry behind this even better. But if you just give me the names, I'm cool with that. So let's see. So we start off with glycerol. Alright, so we start off with glycerol. So this is the glycerol molecule. It has 3 carbons and 3 hydroxyl groups, 3 OH groups. Alright, so 3 carbon structure with 3 OH groups. And the first thing we want to do with glycerol is to turn it to glycerol 3-phosphate. Now this is a phosphorylation reaction. So the enzyme that catalyzes a phosphorylation reaction is a kinase. Excellent. Alright, so you see how sometimes biochemistry can make life simple, right? So you are phosphorylating glycerol to glycerol 3-phosphate. Therefore, the enzyme you're using is glycerol because the substrate is glycerol, and kinase because kinase are the subclass of enzymes that will add a phosphate group. And always remember that a kinase will take the terminal phosphate from ATP and transfer it to the substrate, which in this case is glycerol, and the ATP becomes ADP. And something I've said many times is that if this is a phosphorylation reaction, you just say ATP is going to ADP. You do not say ATP is going to ADP plus PI, because the PI, that phosphate, is being added to the substrate, in this case glycerol, and is being added to carbons 3 on glycerol to give you glycerol 3-phosphate. So look out for that. Once you have the glycerol 3-phosphate, then you do an oxidation reaction and convert the glycerol 3-phosphate to the compound called DHAP, which stands for dihydroxyacetone phosphate. Now this is an oxidation reaction. So you're using an oxidoreductor enzyme, alright? And in this case, it's glycerol phosphate, or it should be glycerol 3-phosphate dehydrogenase. So glycerol 3-phosphate dehydrogenase is the name of the enzyme that converts glycerol 3-phosphate to dihydroxyacetone phosphate. And this is an oxidation reaction, alright? Now a student asked me just the other day, and it's a very good point that she made, and that's you know, how is this an oxidation when the NAD plus went to NADH? It meant that the NAD plus gained hydrogen. So isn't that a reduction reaction? And my point here is that when we say that this reaction is an oxidation reaction, we mean in respect to the substrate and not really the cofactor. Alright, so this glycerol 3-phosphate, alright, if you look at the differences with the two chemicals here, the two molecules here, this alcohol group was oxidized to a keto group. Alright, so that's the oxidation reaction. So it's an oxidation in respect to the substrate. Alright, so please learn this reaction. It's a very common question where we ask you to give the enzymes and the reactions that are responsible for making glycerol a glucogenic precursor. Now once you form DHAP, now this word here, this molecule here, DHAP, that should be sounding very familiar. DHAP is an intermediate in glycolysis. Alright, and there's on a side note, once you could get an intermediate of glycolysis, it means that you can go your way up to make glucose. So let's remember that. So once you convert your startup molecule, your non-carbohydrate molecule, like in this case glycerol, and you can turn it into an intermediate of glycolysis, then you're on your way, brother. You could go right up and make glucose. And we'll talk a little bit more about that later on. Lactate as a glucogenic precursor. Now how that works is that we are converting the lactate to pyruvate. So it's lactate plus NAD plus. It's a reversible reaction to give you pyruvate plus NADH plus H plus. And I ask you here, what is the enzyme that catalyzes this reaction? The reason being is that when we looked at glycolysis and we looked at the 3 fates of pyruvate, one of the fates of pyruvate was to convert pyruvate to lactate. And the enzyme that did that, catalyzes that reaction, will also catalyze this reaction, because this is basically the reverse of what we saw in glycolysis. So I'm not going to tell you the name. I want you to go back to your notes and see what the answer is for yourself. You know, you can hit me a little message on YouTube and tell me what's the name of the enzyme. Let me just make sure everybody's following on the same page, right? So once you know the name of the enzyme, please type it in the comments on YouTube so that I will see that you all are getting it right. Alright guys. So remember, I was telling you all that glucogenic amino acids. Now what are glucogenic amino acids? Well, glucogenic amino acids give rise to pyruvate or are converted to TCA intermediates which generate OAA. Now what do these things stand for? TCA stands for the tricarboxylic acid cycle or the Krebs cycle, and the OAA stands for oxaloacetate. So basically what we are saying is that visualize an amino acid in your mind. Right, this amino acid will have a carboxylic group and an amino group. What we are saying is that we dispose of the amino group and we take the rest of the carbon skeleton, and once you can make pyruvate out of that, or you can make any of the TCA cycle intermediates which will generate oxaloacetate, you can eventually get back to glucose. Alright, now here's some good news. All of the 20 common amino acids that are necessary for good health, 18 of them are glucogenic. Alright, in fact some of them are what we call, could be both glucogenic and ketogenic, right? But those details are not necessary. All I want you all to know is that out of the 20 common amino acids, 18 of them can be metabolized and give rise to glucose. There are two amino acids that are solely ketogenic. Alright, and all I will ask is that you remember those two. So you know that the other 18 are glucogenic. But there are two of them, alright, out of that 20, that are solely ketogenic. All that we try with them, we will never be able to metabolize them in no form or fashion and get glucose. And those two amino acids that will never give rise to glucose will be leucine and lysine. They are solely ketogenic. Alright, the other 18 amino acids will be glucogenic. Alright, so just remember there's a nice multiple choice that comes along the way. Okay? Alright, so let's recap. We did glycolysis before, and we know that glycolysis is going from glucose to pyruvate. And now I'm telling you all that gluconeogenesis is kind of the reverse of glycolysis, and we're going from pyruvate to glucose. So again, glucose to pyruvate was glycolysis, pyruvate to glucose, gluconeogenesis. So the question now is this: is gluconeogenesis the reverse of glycolysis? Well, not quite. Alright, and let's look at some facts here. Now we all remember these three famous guys. These are the non-reversible enzymes in glycolysis. Alright, you have hexokinase, and then you have the main regulatory enzyme in glycolysis, which is PFK1, and you have pyruvate kinase. Three of these enzymes in glycolysis are what we say non-reversible. Alright, three of them. Now let me ask you a question. Can you remember how many enzymes there are in glycolysis? I hope you all are shouting out 10, because that will be the right answer. So just to recap, there are 10 enzymes in glycolysis. There are 10 glycolytic enzymes. Three of them are what we say they go in one direction only, they are non-reversible. And the three of them are hexokinase, PFK1, and pyruvate kinase. The other 7 are what we say they are reversible. Now in terms of change in free energy, the reversible enzymes, their change in free energies is close to 0. But for these three reactions that we are looking at here, the hexokinase, PFK1, and pyruvate kinase reactions, their change in free energy is very negative. And that's good news for glycolysis, because a very negative change in free energy means that these reactions are spontaneous. Alright, they are very energetically favorable. Alright, so these three reactions here are energetically favorable. They're very energetically favorable. But the problem now is that if we want to go in the reverse direction, which is basically what we are trying to do in gluconeogenesis, and we use these three enzymes, if we used to go in the reverse direction, the change in free energy numerical value wouldn't change, but the sign will change. So now if you go in the reverse direction, it's going to become very positive. And what that means is that there's going to have a huge activation barrier in the reverse direction. Alright? And that means that it's going to be very energetically unfavorable. You're going to take a large amount of energy to overcome this activation barrier in the reverse direction. Alright, so the cell now is in a predicament. It needs to make glucose for the brain and for the erythrocytes. But if it was to do the reverse of these three reactions, it's going to take a lot of energy. So the cell has done some bypass reactions to bypass these three enzymes and still convert pyruvate to eventually glucose. Alright, now I mentioned 7 enzymes before. Alright, those 7 enzymes, the change in free energy was close to 0, meaning that in one direction is 0, in the other direction is close to 0. So they could go in both directions. So those 7 enzymes are common in both glycolysis and gluconeogenesis. It is these 3 that will be unique to glycolysis, and we will need some new enzymes to bypass these 3 enzymes here. Alright, so we're going to look at that shortly. So let's recap. So we have glycolysis. So we have glycolysis on this side, gluconeogenesis on this side. And let's look at something here. So glucose going to pyruvate. We already know that's from glycolysis. But now we want to go from pyruvate to glucose, which is gluconeogenesis. There are 7 enzyme reactions that are common between glycolysis and gluconeogenesis, but there are 3 of them that we need to bypass. So the first bypass reaction. So when you go from PEP to pyruvate, that would have been in glycolysis, you would have used pyruvate kinase. Right? Now that you're going in the reverse direction, you're going pyruvate to phosphoenolpyruvate, which is PEP, you're going to have to use 2 enzymes to bypass this one. So the 2 enzymes in gluconeogenesis that you're going to be using will be pyruvate carboxylase and another enzyme called PEPCK. And the PEPCK stands for phosphoenolpyruvate carboxy kinase. So you're using these 2 enzymes to bypass the glycolytic enzyme pyruvate kinase. Now as you go up now, 1, 2, 3, 4, 5, 6, these enzyme reactions here, their change in free energy was close to 0. So we could use these enzymes in both glycolysis and gluconeogenesis. Now we reach another sticking point here. Fructose 1,6-bisphosphate going to fructose 6-phosphate. Now in glycolysis, going in this direction, fructose 6-phosphate to fructose 1,6-bisphosphate, we would have used PFK1. But remember I told you this has a huge negative change in free energy. So if you was to use this enzyme and do the exact reaction in reverse direction, it's going to have a huge activation barrier. So we have bypassed this reaction by using this other enzyme called fructose 1,6-bisphosphatase. Alright, and then this is the 7th enzyme that will be common in both of them. Can you tell me the name? I'm not going to say it. Go and look over your glycolysis. And finally, the other irreversible enzyme reaction. In glycolysis, when you're going from glucose to glucose 6-phosphate, you use hexokinase. But now that you want to go from glucose 6-phosphate to glucose, you cannot use hexokinase in the reverse direction because of that huge activation barrier. So you use another enzyme called glucose 6-phosphatase. Alright, so these are the enzymes that bypass the glycolytic reactions. Alright, so just to recap, there are 3 steps unique to glycolysis and gluconeogenesis. There are 3 unique enzymes for glycolysis. They are hexokinase, PFK1, pyruvate kinase. There are 4 unique enzymes for gluconeogenesis, which are pyruvate carboxylase, PEPCK, fructose 1,6-bisphosphatase, and glucose 6-phosphatase. The other 7 enzymes that was used in glycolysis can and will also be used in gluconeogenesis. Alright, so guys, you should be, a point I always make in class is that for you to understand gluconeogenesis, you need to understand glycolysis. Alright, you can't do one without the other. So the enzyme that bypasses hexokinase will be glucose 6-phosphatase. The enzyme that bypasses PFK1 will be fructose 1,6-bisphosphatase. And for pyruvate kinase, they need 2 enzymes to bypass that one, which will be pyruvate carboxylase and phosphoenolpyruvate carboxy kinase. Now remember, in gluconeogenesis, you're going in the reverse direction. So this here will be your first bypass reaction, and that's described in part 2. And then these other 2 guys are described in part 3. So this will be a second bypass reaction, third bypass reaction. Alright? And remember that you have 7 common enzymes that are common in both glycolysis and gluconeogenesis, and they are phosphohexose isomerase, aldolase, triose phosphate isomerase, glyceraldehyde 3-phosphate dehydrogenase, phosphoglycerate kinase, phosphoglycerate mutase, and enolase. Alright, and this here represents some very common multiple choice questions, and I will tell you, read your question very carefully, because sometimes they might ask you, well, name 3 enzymes that are unique for glycolysis, or they might tell you to select some enzymes that are unique for gluconeogenesis. So these will be the top guys up here. Or they might have asked you, well, give some enzymes that are common in both glycolysis and gluconeogenesis. These will be these guys here. So be very careful with the wording of the question. Read your question very carefully, especially those multiple choice. Alright, they could trick you. So read the wording. Are they asking for unique enzymes, or are they asking for common enzymes, and for which pathway. So be very careful when looking at these questions. Alright, so we have come to the end of part 1. I hope you are a little smarter in biochemistry now because of this. And if you are, please like the video, subscribe to the BiochemJM YouTube channel, and of course guys, we will love to hear from you all, so send your comments our way. I know we'll be looking forward to hearing from you guys. And as usual, we're working hard over on this side, you know. More videos coming soon. Alright, so take care guys, and let's keep at it, and we'll talk soon enough. Take care. Bye.